Good afternoon, everyone. Welcome to my talk about Zenoh PX4 for multicast distributed networking between PX4 and ROS2. Could I ever get a raise of hands if people know what Zenoh is? Okay, a lot. I'm surprised. And people would know what multicast is? Okay, well, we got some informed crowd here, that's good. So let me introduce myself. So I'm Peter van der Perk. I work for NXP Semiconductors inside the CTO Systems Innovations, and we got a department there working on mobile robotics. So what we do is we make reference designs already tailored for robotics use cases. Examples could be like the PX4 vehicle management unit, but also NXP does a lot in CAN and Ethernet nodes, battery management systems. And most of these reference systems, we try to utilize open source software to have demonstrators over that. Also inside, we have the NXP Hover Games, NXP Cup, where we try to engage with STEM programs and students for the Hover Games. Just a very quick introduction to Publish and Scribe. So the concept of Publish and Scribe, you have a publisher, you have a topic, and you have a subscriber. So in PX4, MUORP is the mechanism used to communicate between different processes and different data, and in ROS2, DDS is used for that. So a very quick introduction into PX4, how it's done. So PX4 runs NuttX. On top of that, we have the MUORP implementation. Then we have different services doing different tasks in between there. We use these topics to communicate. What you see now recently is that this is getting expanded to the ROS side as well. So we have a bridge. We have an agent, and we can translate that, and we can have more advanced autonomous functionality on top of ROS2, and we can translate transparently. Although we have lots of different middleware there, and they kind of have their trade-offs. So if you look at what has been used in ROS1, it's called TCP ROS or ROS1, and this was more like a brokered middleware. So we had to have a ROS master. You have to set up communication. If your ROS master was down, your communication was down. With ROS2, DDS solves it, so you have more peer-to-peer communication. You have even way more better QoS functionality. Although DDS tends to be also, because of flexibility, quite complex, also quite heavy compared to microcontrollers. And Zenoh is an interesting alternative that also implements a publish subscribe mechanism, which also supports peer-to-peer, but also brokered communication, which can also simplify that. And as of last week or 2 weeks ago, ROS2 is also looking at implementing Zenoh as an alternative middleware, so you can even have native support. So a very quick introduction on Zenoh. So what Zenoh does is pretty much all the networking. So you think about, you have your different data links, TCP, UDP, and on top of that, Zenoh has a routing, packet switching. So you can combine your packets and route it through to the other side. And the thing I really like about Zenoh, it's also skills to microcontrollers. I've been experimenting also with DDS and microcontrollers, but I need to get the biggest, heavy ones just to be able to flash it, run it, and even if I have multiple topics running, I just run out of RAM. So also something very interesting about Zenoh is actually the flexibility in the topology. So Zenoh does peer-to-peer communication like we're used to DDS. But Zenoh also supports like a router functionality. So you can have a router, you can have clients connected to it. You can even mix different protocols. So you're limited to only using TCP because you have to go with the internet, or other means you can mix that. So, and then also the next part is then you can even have some meshing as well. So peers can route to other peers. And what makes it interesting? Well, you can combine these to like one huge system. And if you think about a drone or a swarm or a drone and ground control station, pretty much everything gets in there. So we can have a system connected to a router, which could be a companion system, but you can have a ground control station. So what you see is kind of like the Internet of Things, or just everything networking can be combined into one system. And it's kind of overwhelming here, but actually, Zenoh makes this quite easy. And if you yesterday saw the Mavlink talk, things can also be cumbersome. And IP networking is a good solution for that. So how does Zenoh to ROS2 bridging work right now? So ROS2 right now is mostly based on top of a DDS. So we can now run Zenoh also on the PX4 Autopilot. And if you want to run connected to ROS2, we have to use a router and a bridge, and we can bridge between the DDS world. And then from this router perspective, it's just one single network. So how is Zenoh implemented on PX4? So PX4 uses MUORP, but actually MUORP is quite close to ROS2 right now. It uses the .message format to define how the messages are specified, and you can already use that transparently inside of ROS. So the nice thing we could do with that is that we ported the DDS serializer of the packets, so we can do now full DDS serialization inside PX4, and then we use Zenoh as a transport. And because of that, we can just reuse all the topics we have right now in PX4 inside the ROS2. And potentially we can even expand some ROS2 messages back into PX4 of that, although there are some limitations there. ROS2 kind of uses like unbounded strings in the messaging format, so we kind of have to think about if we have a big payload, what would be the upper bound of that. So I think that's something for the future, and maybe it's also very interesting to have that discussion in the aerial work group, what would be the intercommunication there. And also something interesting about what we did in the Zenoh implementation now on PX4 is that we pretty much have implemented all messages. So if you have played around with the DDS XRCE mapping, you have to change your YAML file, make custom mapping there, you have to recompile. I've decided I don't want to do that anymore. I just want to have one binary. You can make a configuration file. You can tell which topics go over where and which topics you want to subscribe to. So how does this work? So there are actually two use cases. So the primary use case I've been experimenting is actually FMU to FMU communication. So if you want to have redundancy or you want to have a fallback mechanism, how do you want to communicate with each other? So what we do use is a switch with multicast. So multicast, to summarize, is typically IP communication is more like point-to-point. You want to send a packet from one IP address to the other IP address. What you can also do is sending out a broadcast, but the broadcast means that everyone is going to receive that. The concept with multicast is you're going to have groups where clients can join the group, and then they only receive the messages in those groups. So Zenoh implemented this multicast. If you have a switch that's multicast capable, that's going to take care of that. Even if you have multiple switches, everything gets routed to IP. So what's the good part about that is if we kind of just multicast our messages, we don't necessarily need a broker anymore. Whereas if you played around with DDS or bridges, you always needed an agent, go back to your microcontroller, but now it's like a fully independent system. And also the nice part is there's no duplication needed anymore. So now I have two FMUs on the network. If I want to add a companion system, I can just add a companion system and it can introspect it. We can run the bridge and we can just see everything going on the network, and it just pops up as a ROS2 topic. So how does that look like? It's pretty much on PX4. I just start up the Zenoh application. It's pre-configured to now publish the RT MUORP messages to the multicast network, and then on side of ROS2, we just run the Zenoh bridge, and in this example, we get the RC input. So this is quite extensive. So we can think about sensor messages, anything else. Right now, the implementation is quite basic, so I'm not doing rate limiting. So if you really daring, you're going to send out your IMU, you're going to have the 1000 Hz IMU data out. Luckily, for now, it seems that it's quite performant. We can also keep up with that data stream, so we're not even overloading FMU with that. But it still needs some fine-tuning. But actually, you could ask, well, why did I implement it? For me, it was mostly interesting to think about, okay, how would a redundant FMU setup look like? So this is more a concept I've worked out. So I have a remote control connected to a microcontroller, and that's going to send out the multicast message of this RC input. It goes to the switch, and then FMU1 and FMU2 is going to receive the same control input. And what I did then as well is that I kind of modified the drone cam messaging so there can only be one master controlling the ESC, but then there's like a fail-safe takeover. And how does that look like? So this is the physical setup of that. So we have the small Ethernet switch in the middle. On the left side, we have a receiver, and controlling from one RC, and then the calculations for the motor and for the steering wheels being done at the same time. So they're both controlling these motors, but now we have a priority system, and if there is a small timeout of 10 milliseconds, the other one takes over. So the ESC is a bit modified for that, but that's just to show the concept. So what happens then if I kill the connection from one FMU to the ESC, or one FMU dies? Pretty much the whole system keeps on working. So in concepts, right now, this is an idea to have like a fully redundant FMU. It could be a software crash or something else. We can always keep on working. And this is very important for a drone, because if you have a rover, you crash, you still have velocity, you might bump into a wall, but for a drone, you quickly go to an irrecoverable state. So that's why we are looking at a potential fallback for that. So kind of overview. So as of this week, Zenoh is in PX4 main. It's based on a bit older version of Zenoh, because they're kind of developing quickly. So you kind of have to bear with me. I still have to write the documentation to make sure that you install the right version, because you kind of have some incompatibilities. Fortunately, right now there's no rate limiting. So also, if you're going to use it for applications, you have to make sure that you're not going to overload the FMU. And yeah, so as of October, there's now the newest release. So hopefully in coming months, I can also implement that one. But actually what's more interesting, I kind of saw the polls already. They were looking at an alternative RMW for ROS2. But as of last week, this got presented. So that actually means that we don't even would have to use the DDS plugin, DDS bridging, which technically can mean that we can just use a flight controller connected to a Linux system, and they can just communicate the same protocol. As far as of now, it's quite in the early design phase. The next ROS release is aimed to have some basic implementation. But I think it's very exciting to have like one network setup, and it doesn't matter if you're running a heavy computer or a small flight controller. But also what is very interesting is we go even smaller and just have a small sensor with an Ethernet connection, and we can just bring this into the ROS world or even into the PX4 world. And we don't have to play around with long I2C wires, the magnetics and other stuff, because if you look at the Ethernet, and specifically automotive Ethernet we work with, it's quite fault tolerant. You don't have to shield your cables, so it would be very nice to be able to use that technology. And also I've been talking with other people, it's like, well, if we have this very advanced networking topology, wouldn't this be interesting for more like cloud communication or ground control communication, and just stream the topics at the rates you want to into your ground control station or to even other platforms? Right now, this is kind of at the beginning, but I'm very curious how people think about can you just have this advanced network topology. Well, this kind of concludes my talk. Feel free to contact me. Any questions? Yes.
You show that it uses cycle reviews, right?
Yes.
So do I have to change on my ROS2 network the RPS cycle to use it, or can I keep the RPS?
I think you can keep it, but you have to be careful with the whole DDS compatibility. So, yeah. Yes?
Can you explain a bit of the problems or challenges with agents and the other?
Yeah, so what I'm mostly working is with systems that have to be able to work independently. And if you kind of have microcontrollers connected to a Linux system and you kind of safety certify your microcontroller, but it has to rely on a Linux system to do your communication, and your Linux system is going to do a kernel oops, then pretty much your whole system is down. So the nice thing about this is more, okay, can I have a fully independent system, and the only thing I have to rely on is my cable for the networking. Yeah.
You said there is no time synchronization yet, right?
Yes.
So if I send from my companion computer any message and I put it last time now, the timestamp, what will arrive on the PX4 side?
So I'm cheating, so I'm gonna inject a new timestamp. So on every received message, I just override the incoming last timestamp. So that's kind of the hack I did right now. The thing is that you can just do like precision time protocol. It's also inside of Nodex. But I didn't want to enable all this stuff right now there. Personally, I'm even looking at the GPTP. So that's even on the Ethernet PHY level, you can do time synchronization. So the question is, like, you want to synchronize a system, but where do you synchronize? More on a high-level protocol, or do you want to have it on a low-level protocol? And also, what would be the needs of the precision of the synchronization? But as of now, there is no good solution for that.
Are you able to say a bit more about the automotive Ethernet?
Yeah, so I don't have really slides about it. So automotive Ethernet is pretty much the automotive industry wanted to have something, a high-speed interface compared to CAN bus. But then they also have the requirements regarding the wiring. So they wanted to have cost-effective two-wire unshielded cables. But if you look at also automotive, you have typically a combustion engine and a spark plug, so you can have EMI interference. So what you have with automotive Ethernet is a differential pair that can handle with all these specs for the automotive use case. So that also makes it very reliable for use in drones.
Will it be possible in the future to also have services created by PX4 and exposed to ROS instead of just always?
So as of right now, you can replicate the RPC mechanism. So the communication stack can already do that. It's now more the question, how much do you want to introduce inside of PX4 to do that? And actually, that's just a question right now is, okay, we're gonna kind of bring ROS2 to the microcontroller field, but which features do we want to have? Also looked at, for instance, the parameter system of ROS2, which is also a service request. But then technically you could have a list of kilobytes, and yeah, where do I allocate it if I'm running a microcontroller with 200 kilobytes? So that's kind of where there has to be some kind of conversions to make it work well, but technically it's possible. Well, if you have any other questions, feel free to contact me. And yeah, if you're crazy enough to try it out, it works already in main. And hopefully I can also publish some documentation fairly soon, probably when I have rebased it to the latest Zenoh to make it work a bit nicer. I don't think you guys want to build your own Rust packages and all that stuff. So, okay.